Hello, statistics students. Here's another video on the basic ingredients for testing with categorical variables, an introduction to section 10.1. So a little bit of review from before we get started. As we've seen in the last few chapters, statistical tests are comparisons between two different views. In one view, if two samples have different means, then it might be because the populations are truly different. In the other view, randomness rules, and this difference is due merely to chance. A sample of people who had watched violent TV as children may behave more aggressively toward their partners when adults, but this might just be due to chance. Or another example, changing the placement of an advertisement on an internet search results page might lead to a greater number of click-through visits to the company that placed the ad. Or this difference could be due to chance. That is, if we were to repeat the study, we might see a very different outcome. In this particular chapter 10, we asked the same questions before. Are the results we see due to chance, or might something else be going on? In chapter 8, we asked this question about one sample and two sample proportions. We now ask the same question with respect to categorical variables with multiple categories. For example, we might compare two categorical variables. The results of popping a batch of popcorn, the result is good, or the result could be bad. For different amounts of oil, no oil, medium amount of oil, and the maximum oil. Or we might compare a single categorical variable with a proposed model. Do the proportions of people hospitalized for swine flu for different age groups match the proportions of people in those age groups in the general population? If yes, this suggests that swine flu affects all age groups the same. One of the nice surprises in this chapter is that only one test statistic is needed to analyze data collected under several different situations. This test statistic can be used to compare distributions of categorical variables, to compare population proportions, and to test whether two categorical variables are independent. This chapter also introduces a hypothesis test that requires no assumptions about the distribution of the population or the sample. So now let's introduce you to this new test and the structure of this test. The statistical questions we ask now with multiple categorical variables are similar in many ways to those we ask of numerical variables. What's the typical outcome? Are two variables associated or not? You'll also see that the basic structure of our analyses are similar. For example, hypothesis tests follow the same 4 steps you learned in chapters 8 and 9, and we're still concerned with whether the observed data match the values we expect under our probability model. However, you'll see that we use slightly different ingredients: expected counts, the chi-square statistics, and the chi-square distribution. Yes, that CHI is pronounced chi, rhymes with pi, with a silent H. The chi-square distribution. To provide a context for our discussion for this new technique, we're going to consider a particular 6-sided die and ask the statistical question, is this die fair? In other words, is each side of a thrown die equally likely to end up on top? Remember, a die has sides 1, 2, 3, 4, 5, and 6 sides, and we roll it to see which one it lands on. We might think that this die is fair because of the symmetry of the die. However, the manufacturing process must be very precise to achieve this. Surely the dice we buy have a few slight defects here and there that would lead to their being biased. We took a die out from our favorite board game and decided to test whether it was fair. Our null hypothesis was that the die is balanced so that each side is equally likely to land face up. The alternative hypothesis was that one or more sides are favored. To test whether this die was fair, we rolled it 60 times. For each outcome, we counted the number of dots showing on top of the die. Before we look at the results of our tossing it or rolling it 60 times, let's think about what the outcome would look like if it were a fair die. If we rolled a perfect die infinitely many times, the outcome should look like figure 10.1, a uniform distribution because each outcome is equally likely. So what this chart is telling us is that to roll a 1, 2, 3, 4, 5, or a 6, there's an equal chance of 1 out of 6 for each respective die. So let's look at our 60 rolls of the die. How did our real die compare to the perfect ideal die? Table 10.1 provides a summary of these data. So rolling a 1 landed 12 times, rolling a 2 landed 8 times, rolling a 3, 10, rolling a 4, 11, and rolling a 5, it landed 9 times, and rolling a 6 landed 10. So remember, each of them have a equal chance of 1 out of 6, and we rolled it 60 times. A fair die, an exactly fair die, would have rolled 10 times for each one of them. So not too far off, but keep in mind we didn't roll it that many times. And the following figure shows the graph of the results with our real die. So we see that the 1 dot had 12 times landing. The dot 2 landed 8 times, dot 3, 10, dot 4, 11, dot 5, 9, and dot 6, 10 times. You can see more clearly from the graph than from the table that we did not get a perfectly uniform distribution. The question now is whether these deviations from the perfect model in 10.1 occur because the die is not fair or are due merely to chance. Comparing the real outcomes to expected outcomes is a fundamental analysis of our chi-square technique. Our approach to solving this problem will be to compare our actual outcomes with the outcomes we would expect to get if the die were behaving as dice are supposed to, giving us roughly equal proportions of outcomes. If the die was fair, behaves as it's supposed to, it would mean that we'd get equal proportions of outcomes. To compare the real outcomes with the expected outcomes, we'll make use of a statistic called the chi-square statistic that measures how far apart reality is from expectation. Next, we'll see that this statistic's sampling distribution, the chi-square distribution, can be found to find the p-values, which would tell us whether we should be suspicious that our outcomes aren't conforming to our expectations. The basics of this approach should sound familiar. It's the same outline we've followed with every other hypothesis test. Some of the details are different, of course, but the approach is the same. And this concludes the video for the introduction to the basic ingredients for testing with categorical variables, in particular the chi-square test.